Hi, I'm Norman Wildberger. Today we're going to continue looking at determinants with a view of applying them to formulas in geometry. So a determinant is a function that inputs a matrix and outputs a number. And although it's rather complicated for a large matrix, for a 2x2 or a 3x3 matrix, it's very accessible and useful. So there's our 2x2 determinant, AD minus BC, and the 3x3 determinant has 6 terms, each involving a product of 3 elements from the matrix. And today we're going to look at several important properties that this determinant function has. The first is that it's a linear function in any row or column. What does that mean? Well, suppose, for example, that we just had a look at how it depends on the first row, A, B, and C. So if we just look in this expression, where are there A, B's, and C's? There's an A there, an A there, a B there, a B there, a C there, a C there. So each term has exactly one element from that first row, and that element is just appearing linearly, just by itself, not raised to any power. In general, if we have a vector v given with coordinates x, y, and z, then a function like this is called a linear function. So something in the form ax plus by plus cz, where a, b, and c are, in this case, just specific numbers. That's called a linear function of the vector v. And it has these two basic properties, that f of the sum of two vectors is the sum of f of v1 plus f of v2. And if you look at what f does to lambda times a vector, you get lambda times what it does to the vector. So this is the definition of a linear function of a vector. And what we're saying here is that when you think of the determinant as simply a function of, say, of the first row, and ignore the other terms, or treat them as constants, then we're getting a linear function of that first row. In particular, if you take the determinant and you multiply one of the rows by 5, then the determinant is multiplied by 5. Or if you multiply the column number 3 by 7, then similarly the determinant is multiplied by 7. That's the linear property of a determinant. Another important property of the determinant is that if you interchange two rows, or for that matter, if you interchange two columns, then the determinant gets multiplied by -1. In other words, it changes sign. Let's have a look at the 2x2 case. So here's a 2x2 matrix. Its determinant is 3 times 5 minus 1 times 4. That's 11. If we interchange the two rows, then the new determinant is 4 times 1 minus 5 times 3. That's minus 11. And that rule works not just for 2x2 matrices, but also for 3x3 or 4x4 and so on. As a consequence of that, if two rows happen to be the same, then the determinant must be 0. Why is that? Well, the determinant, whatever it is, must have the property that when you interchange the two rows, it stays the same, because the two rows we're assuming are the same. But if the determinant and its negative are actually equal to each other, then the only way that can happen is if the determinant is 0. So that follows from that previous property. And now, putting the various properties together, we get this very useful rule, which actually is very helpful in calculating determinants. It is that if you add a multiple of one row to another, then the determinant remains unchanged. So for example, have a look at this determinant. This is an alternate notation for a determinant. So instead of writing det, if we write square brackets like that, it means determinant. Okay, so the determinant here is 4 minus 3, that's 7. And this matrix here is obtained from this one by adding the first row to the second row. So we're adding a multiple of the first row to the second row. So the 1 plus minus 1 is 0, and the 3 plus 4 is 7. And what's happened to the determinant? Now it's 1 times 7 minus 3 times 0. It's still 7. So whenever you add or subtract a multiple of one row from another, you get the same determinant. And in fact, that also applies if you work with columns. If you add a multiple of one column to another, the determinant stays unchanged. Our fifth rule is that if the matrix is upper or lower triangular, then its determinant is the product of its diagonal entries. So what does that mean? Well, for a matrix to be upper triangular, it means that all of its non-zero entries are either on the diagonal or above the diagonal. Or, put it another way, everything below the diagonal must be 0. That's called an upper triangular matrix. And we're saying that if you want to calculate the determinant of such an upper triangular matrix, then it's particularly simple. It's just 2 times 3 times 7, which in this case is 42. Now if the matrix is upper triangular, like this one, how can we place 3 rooks on the chessboard so that none of the rooks are in this 0 area? So if one of the rooks is in this 0 area, then the product of those elements is going to have to be 0, and so it won't count. So the only terms that are not 0 are the ones where the rooks are in these positions right here along the diagonal. And that's a valid argument that extends also to the 4 by 4 case, or the 5 by 5, and so on. So that's a rather general rule. And now we come to the sixth and the most important rule, which is one of the most loveliest elementary facts in mathematics. That the determinant of A times the determinant of B is the determinant of the product matrix A times B. So here's two 3 by 3 matrices, and I'm going to show you how to multiply them to get this 3 by 3 matrix. The basic operation is to understand how to multiply a row by a column to get a single entry. So let's just concentrate on that. What is the product of this row times this column? What you do is you multiply the first element here by the first element here. That's minus 1. The second element times the second element. That's 15. The third element times the third element. That's 28. And then you add those three numbers. Minus 1 plus 15 plus 28. That's 42. And why do we put the 42 right there? Because we had the first row and the third column. First row, third column. Over here, first row, third column. So there are 3 possible rows you could choose, 3 possible columns you could choose, and so there are 9 possible such row times column products. That's how you define the product of 2 matrices. Now the determinant of this one, you can check, is 86. The determinant of this one is 76. And the determinant of this one, 6,232, is exactly the product of 82 and 76. So the determinant of this times the determinant of this equals the determinant of the product matrix. Please have a go at computing some matrix products. Start with 2 by 2s and then work your way up to 3 by 3s and compute determinants and check this very important rule. You might even try to figure out if you can prove this rule, say in the 2 by 2 or even in the 3 by 3 case. It's an excellent exercise. Next time we're going to take this knowledge now of determinants and go back to our geometry and see if we can calculate some interesting determinants that come up in rational trigonometry. I hope you'll join me for that. I'm Wildberger. Thanks for listening.